easy.
We're gonna have a really small belly
You
fest.
have a really baby pack.
They said she's sick.
Oh, she's.
Well, that's a lot of work.
Our math class is gonna have 4 people in it.
Well, ballets.
Ballet. Then it'll only be like 1 person.
Wait, don't we have, what's today's schedule? It's like.
We have the stretch video. Like, we don't have stretch with Megan, because she's gonna be in the meeting.
Right.
And then we have class and completion.
Well, like,
from
right
2:30,
on
and
the-
then we have
Yeah,
school
we
proper
are.
from 2:45 to 2:45.
Awesome.
We're done.
How you said mid.
So I start coming down.
I want to find out where I see the numbers, I can like prepare myself
Me
mentally.
too. She said that, apparently I didn't hear this. Apparently I didn't hear this, but she wants us to perform 2 pieces in the gala, which has never
Yeah.
happened in RDA history.
She said 2 to 3.
Yeah. No, in the gala, not 2 to 3, like,
She
like
means
2 to 3 in general, but 2 in the gala.
Sure
for
that that's
sure.
never,
Yeah.
she said 2 or 3.
In the gala? No, I didn't,
Yeah, she said in the gala.
I don't think that's ever happened before.
Pretty sure.
Yeah.
I got it.
I'm sure out of like every single, like, it's been going on for like how many years and
The
like all the
Oregon
different
history.
bits
really
states.
I didn't think it was the gala, I just thought it was like overall.
I think she said gala.
Oh, she did,
Yeah, cause it's.
That's crazy.
Cause she wants everyone to
Is
see
that,
us.
I don't think that's possible though. Because usually for RDA. I love that movie.
Anything is sorry, I can just believe.
Is that an Alice in
From the
Wonderland quote?
Cinderella story.
It's from, yeah.
It's a good one.
He has like actor
And he's like, and then the actor is called Believer. And then he like, and it shows his face like clear and it's like, anything is possible.
I like when he's first doing it, I think more nervous though.
I know. Anything.
You'll be okay, you have me
Okay.
and Lauren,
Alright.
I don't know where I'm going with it.
Let's get down to work here. So, don't forget, please, I mean, I'm trying to gently forewarn you here that that packet through Friday has a lot of stuff in it. So I'm giving you gentle forewarning because if I were you, I would not wait to start getting work done on that, because you may, you're not gonna be able to go just smoothly through the entire thing. I'll just tell you that right now. Like, it is a smooth packet in that it covers things from chapter 1 through chapter 12, and stuff from chapters 12 and 14 on the first page. It's probably not all right here in the front of your mind. So know that you're gonna encounter difficulties as you go through that. And prepare, plan your time to attack that accordingly, because you're gonna wanna have some time set out for that. So let's, let me discuss freezing point depression and boiling point elevation in a little bit more detail. I'll use boiling point elevation as my reference point. And then we'll see a problem that involves numbers here to give you something that would be testable. Remember, your test in this class is next Tuesday. Now remember, when you just have water molecules, it's easier to boil than if you had water molecules and something else. If you just have water molecules, easy to boil, all you have to fight is vapor pressure and internal attraction. But when you have other particles dissolved in, it's harder to boil. Now, for any substance, it has been experimentally determined how the boiling point will change based on the concentration. And I can give you an example of this. For water, the boiling point elevation constant is 0.51 Celsius degrees per molar. So a 1 molar solution increases the boiling point 0.51 Celsius degrees. 2 molar solution, twice that, almost a whole degree Celsius. But now let's think about this for a second as well, because if we're going to determine the molar concentration when we're doing the boiling point here, the molar concentration depends, this is, I should say, for boiling point elevation and freezing point depression only. The molarity depends on the number of particles in the water. Strictly. How many particles do we have dissolved in the water? The more particles we have dissolved in the water, the harder it's going to be to boil the water. The more the boiling point's going to be elevated. The more you're going to have to excite those water molecules to get them to overcome vapor pressure, to overcome atmospheric pressure, overcome internal attraction, and overcome bombarding into their neighboring particles. Now, why do I say it depends on the number of particles for freezing point depression and boiling point elevation? Why do I even bring this up? Well, think. If we are dissolving something like sugar, which is a covalent molecule, the covalent molecule stays together. So an example of something that could dissolve in water would be like sugar. And if we dissolve sugar in water, it stays together as C6H12O6 and just gets surrounded by the water. I'll just draw a single diagram here to show that there's water surrounding it, but the sugar molecules stay together as a whole. This is for a covalent molecule. But if we have an ionic compound that we're dissolving, we know what happens whenever the ionic compound gets dissolved. We've seen this in a couple cases where we try to dissolve salt in water, or at least try to visually represent it. The chlorine atoms separate from the sodium, or the chlorine ions separate from the sodium ions, and then you have the water molecules surrounding. But my point is, with sodium chloride, for every one sodium chloride molecule, you're getting 2 particles dissolved in your substance whenever it's 2 particles dissolved in your water whenever that substance disassociates. Whereas your sugar molecule doesn't break apart. Now I'll say this because if the molar concentration of your sodium chloride is, let's say, 4 molar, you're going to have a 4 molar solution of sodium ions and a 4 molar solution of chlorine ions. That's going to combine to be an 8 molar solution of ions. Because 4 moles of sodium chloride would break into 4 moles of sodium and 4 moles of chlorine. Each particle gets broken in half. Imagine if we had a stack of books that we ripped in half. If you started with 12 books and you ripped each of the books in half, you're going to end up with 12 halves on each stack. That's a total of 24 pieces. Same thing here. If you had 4 pieces of sodium chloride and you break it apart, you're going to have 4 sodiums, 4 chlorines for a total of 8 particles. What if you had like calcium chloride? I mentioned this because the salt trucks will use calcium chloride on occasion because this will break into a calcium ion and 2 chlorine ions. So this guy's breaking apart into 3 pieces. So if you had 4 molar solution, 4 moles per liter of calcium chloride, each liter has 4 moles of calcium chloride. That would be 4 moles of calcium and 8 moles of chlorines. Combine that solution would be a 12 molar solution of ions. So just to be clear, a 4 molar solution of NaCl makes an 8 molar solution of ions. And this is what's important whenever you're considering boiling point elevation and freezing point depression. We said as well, a 4 molar solution of calcium chloride, that's going to have 3 particles to break into. This is an ionic compound. Ionic compounds will break into ions. This makes a 12 molar solution of ions. But I also want to make the point here, in addition to these 2 statements that I made, up above we could say a 4 molar solution of anything covalent makes a 4 molar solution when dissolved. Or I'll say a 4 molar solution of particles. Why is the covalent compound have the same molarity of solution as molarity of particles? Well, because each particle does not break apart. So you're going to have as many particles as you started with. The books are going to remain whole. Whereas in the case of the sodium and chlorine, you're going to be breaking those things apart. So 4 moles of an ionic compound would turn into at least 4 moles of particles because you're always going to be breaking apart. Whereas 4 moles of a covalent compound is always going to be 4 moles of particles because the compounds don't break apart. So let's give an example of this. What is the boiling point? Of 100 grams of water with 25 grams of magnesium carbonate dissolved. And we would be told here in this problem that the boiling point elevation constant for water is 0.51 degrees Celsius per molar. So the more concentrated, the higher the boiling point. We know as well the normal boiling point of water is 100 degrees C. You should know that from previous things. So every molar we have, we're going to increase 0.51 degrees Celsius. Now, let's figure out first what the molarity of magnesium carbonate is. Then let's figure out what the molarity of the ions is, because that's what's going to matter. We care how many particles we have. And in the case of the ionic compounds, you're going to break into multiple particles. So let's figure out the molarity of the solution. Molarity is what over what? Molarity is moles of solute over liters of solution. So, how many moles of solute do we have? Let me ask the first question. What is our solute? Our solute is magnesium carbonate. Okay, now we need to find that in terms of moles. That's the question. We need that in terms of moles. How are we going to take 25 grams of magnesium carbonate and turn it into moles? What are we going to use? Periodic table, okay? So first off, let's look at magnesium. Well, carbonate, if you recall, is a polyatomic ion. So this is going to be an ionic compound. What's magnesium's ion? Look at his location on the table. What's he going to be? Positive? Positive what? Positive 2? Because magnesium is in column 2 and has 2 electrons, he'll choose to get rid of those electrons and become a positive ion. When you lose the electrons, you're going to lose negative charge and become positive. And carbonate is CO3, and its charge? 2 negative. So when you look at this ion here, when you look at this compound, you're going to have the ions in a 1-to-1 ratio, magnesium carbonate, MgCO3. So our formula, MgCO3, we can go to the periodic table and find out how much 1 mole of that weighs by saying there's 1 magnesium, 1 carbon, and 3 oxygens. 1 magnesium is 1 times 24.31. 1 carbon is 1 times 12.01. And 3 oxygens is 3 times 16.00. So we just add that together. 24.31 plus 12.01 plus 48. And we get 84.32. That's the number of grams per mole. That's what the information on the periodic table gives you for the mass of the atom, or the mass of each of the atoms that make up that compound. Now we know we had 25 grams of that. If there are 84 grams in a mole, we can figure out how many moles that is by saying 25 grams of magnesium carbonate is what we have, and we know that there are 84.32 grams in 1 mole of that substance. So that division will give us some number of moles for the number of moles of magnesium carbonate. We're going to use that in our molarity formula. So how many moles do we have? 0.3, okay? 0.3 moles. How many liters of solution do we have? Well, we've got 100 grams of water. What does that mean? How can we get from grams to liters with water? Anybody remember? Olivia? 1 gram is 1 milliliter, correct. And think about that, a gram is a very small amount, and a milliliter is also a very small amount. Both of those line up nice. It's not 1 gram per liter, it's 1 gram per milliliter. So we have 100 milliliters of solution, and 100 milliliters with 1,000 milliliters in 1 liter is just 0.1 liters. So put that together, we have a 3 molar solution of magnesium carbonate. Now, is magnesium carbonate ionic or covalent? Ionic. And that means that when it drops in the water, it's going to break apart into magnesium ions and carbonate ions. So what is a 3 molar solution of the compound becomes twice that of the ions. So we can look at the formula here. Magnesium carbonate will break apart into magnesium and carbonate. So if we have a 3 molar solution of magnesium carbonate, each of these we're going to break in 2 pieces. So for every mole of magnesium carbonate, we're going to end up with a mole of magnesiums and a mole of carbonates. Put that together, that's going to be a 6 molar solution of particles. And that's what matters when it comes to boiling point elevation. It matters how many particles you have, not what types of particles they are, but just how many. And how many is different for covalent molecules that don't break apart than for ionic molecules that do. So if you ever encounter an ionic substance, you're going to have to express the solution in terms of the number of particles, which will require you to multiply by some factor depending on how many particles you break into. But now, if we have a 6 molar solution, we know that the boiling point constant is 0.51 Celsius degrees per molar. So if we have a 6 molar solution, we know per molar the temperature change is 0.51 degrees Celsius. Look at that relationship there, 0.51 degrees Celsius per molar. Well, that means my 6 molar solution is going to have 6 times that number of Celsius degrees adjustment, and 6 times 0.51 gives you 3.06. And that's how much the boiling point's been elevated. If the boiling point was 100 degrees, now the boiling point is 103.06 degrees. There's evidence. There it is. Okay. Do you think you could do that on your own? No? No? Okay. Well, we're not ready for our test yet then, at that point, so keep that in mind. Let's do another one. What's the freezing point of 250 grams of H2O with, let's say, 40 grams of, let's say, lithium oxide dissolved? You would be told what the freezing point constant is for water. I'm going to grab that here for you. The freezing point constant, 1.86 degrees Celsius per molar is the freezing point depression constant for water. Now, if they're asking for the freezing point, if you can figure out the molarity of the solution, you're basically done. Because once you know the molarity, you know the effect on the freezing point, then you know the actual freezing point. Because you know that the normal freezing point of water is 0 degrees Celsius. So for every molarity number, we're going to decrease our freezing point by a Celsius degree. So if we can figure out the molarity, then we're done. We can convert into Celsius degrees and the problem's over. So let's try to figure out the molarity of this solution. Molarity, moles of solute over liters of solution. Our solute is lithium oxide. So we want to know how many moles of that we have. We know we have 40 grams of it. So let's figure out how many moles that is. Lithium oxide. What ion does lithium make? Lithium makes a +1, because lithium has one free electron. And oxygen will form what ion? -2. So when you put that together, you're gonna need 2 lithiums for every oxygen. That's gonna be Li2O. Go to the periodic table. 2 lithiums and 1 oxygen. 2 lithiums is twice 6.94. 1 oxygen is once 16.00. So that's gonna be 13.88. No, 13.88. And 16.00, add them together, 29.88. That's the number of grams in 1 mole of lithium oxide. So if we have 40 grams of lithium oxide, and we know that there are 29.88 grams in a mole, we can get from grams to moles, and now we have just the nugget of information we need for our molarity equation. So 40 divided by 29.88 gives you 1.3.
Oh my goodness.
Say what?
Oh, there are big pieces of ice falling
Oh,
from the
it's
sky.
fine.
It looks like hail.
The sky is falling.
Yeah, those are some pretty large pieces of ice.
Oh, wow.
Really, it's like hail.
You can
It
hear
is.
it, yeah.
I know, I thought the window was like cracking over here. I'm like, oh
Right.
my god, what's happening?
Yeah, little ice nuggets falling from the
Oh,
sky.
nuggets.
Nuggets.
They were gold nuggets.
That's awesome. I'd see you
Shoot
like.
meteor nuggets,
Yeah,
$2,000 an ounce.
there you go.
I'd see
Yeah,
you
that
like.
meteor that came in Russia, there's people apparently that are like flew to Russia to find scraps of the meteor. Because
Yeah.
meteors, the precious metals in there, $2,000 an ounce. And
That's
gold,
kind of awesome.
gold is like $1,900 an ounce.
Yeah,
So
an
it's-
ounce is like 28 grams.
Yeah, which
So it's
is,
not a lot.
that's, yeah.
Like,
So if you just find some dust, I mean, you're gonna be able to put yourself to,
yeah, we'll
Yeah.
just pan.
Did I lie? An ounce is 28 grams, right?
maybe,
That-
Google it, I don't know, it sounds right.
Okay, I am gonna Google it.
16 ounces of 1 pint.
Yes.
They're wrong, right? But yeah.
Random
Yay!
Sorry.
So, no, that's okay, this is good. So we have,
I was right.
what is it? You're right?
Said I was right.
So, so 40 grams of the solute we found to be 1.3 moles of solute. The liters of solution, well, we had 250 grams of water. That's 250 milliliters, which if 1,000 milliliters is a liter, that's 0.25 liters. You'll get really good at milliliter to liter conversions through this chapter. Just hop the decimal thrice if you want.
Holy Christ.
Right, 3 times. 0.25 liters. So we do the division, we can figure out the molarity of the solution. 1.3 divided by 0.25, that's what, 5.2. 5.2 molar. Now, it's a 5.2 molar solution of Li2O. That does not tell you, though, the molarity of the solution once everything's dissolved. That just tells you how many moles per liter of the substance we have. Now, is lithium oxide an ionic compound? Is lithium oxide an ionic compound? Why do you say no?
Because the name of it tells you what it's for, maybe?
Ionic compounds are made of a metal and a non-metal. Covalent compounds are made of a non-metal and a non-metal. So when you look at this guy, lithium oxide, metal, non-metal. Look how we put it together, ion, charges. ion. So if you're ionic, when we drop the lithium oxide into the water, it's gonna break into lithium ions and an oxygen ion. So what drops in as one particle becomes 3, right? So what was a 5